Hello my people, I hope we're doing well. This is video 3 for Sum Difference IDs. In this video we'll be dealing with verification problems and a couple of equations. So let's go ahead and get started. This one right here. Now if you know anything, once you become familiar with the sum and difference formulas, you should be familiar with the fact that tangent of a difference is a difference over a sum, right? And so, tangent of u minus v is tangent of u minus tangent of v over 1 minus tangent u tangent v, or sorry, 1 plus. Now, it should be very evident the fact that this is of the same structure as this. It's a difference over a sum. So if I were to take this right-hand side and apply that difference identity, what I will wind up getting is sorry, trying to write and talk at the same time. You think I would be better at that by now. When you evaluate the tangent of pi over 4, both of those turn into 1, and you get 1 minus tangent over 1 plus tangent, and you're going to try and change that into this. Now remember, when they have exactly the same structure, the question you should be asking yourself is there something that I can simply multiply the numerator and denominator by that will transform, and that one thing will transform all the terms into what I need them to be? And the answer for this one is yes, right? How do I turn 1 into cosine? Well, I multiply by cosine. How do I turn tangent into sine? Well, I multiply by cosine. How do I turn 1 into cosine? Well, I multiply by cosine. How do I turn tangent into sine? Well, I multiply by cosine. So the strategy must be that I multiply both the numerator and denominator by cosine and arrive at cosine theta minus sine theta over cosine theta plus sine theta, and that is indeed identical to the right hand side, and my verification is a success. Yay! Now, this one right here may seem complicated and rather arbitrary, but I assure you it's not. This is actually a foreshadowing for a very specific limit that we will entertain right at the beginning of calculus. So you'll see this again soon, which is of course why textbooks include this in why pre-cal textbooks include this in their sum and difference section, and of course why I'm showing it to you right now, right? Well, this side over here, the ability to simplify that is going to be kind of difficult because you're going to have to know exactly how things are going to fit back together. Let's go ahead and take a wrecking ball to this side and sort of unsimplify it. So let's take that, and basically what I'm thinking about doing is, of course, the only thing that can be changed right now is that. So I have sine x cosine h plus sine h cosine x minus sine x, all of that over h, right? And of course, that binomial is what came from the sine x plus h. And now all I need to do is figure out, can I reorder all of this stuff to come up with this? Well, I see the fact that they have broken it apart into two pieces, right? This side has sine multiplied by that. So I see the fact that I have, let me color code this. I have this sign right here, and I have this term right here that has a sign in it. Why don't I actually bring those closer together? So I'm going to swap these two terms, and I'm going to, all right, I'm going to get back to using black. Sine h cosine x plus sine x, and actually once I put those together, let's go ahead and factor out that cosine h minus 1. And now obviously I'm going to separate those, so let's go ahead and just separate those into two separate fractions. And then all I need to do in order to make it look like this is basically take the x, like the trig expression involving the variable x, out of the expression and plop it down in front. And that'll make sense why we're doing that. Sorry, cosine h minus 1. It'll make sense why we're doing that the moment that we play around with this in calculus, because it actually helps us do something very, very specific. And so this is, of course, identical to the right-hand side, and yay, I have verified. Okay, well, you know, that one is a little bit forced because it's a very specific foreshadowing one. This one is more sort of the ordinary, hey, let's play around with these identities and see what we can get. This is the cosine difference plus cosine of a sum. And so let's go ahead and just use both of those. Let's expand both of them. And we know that this difference is going to wind up being a sum, right? And so this right here becomes that binomial. I know that this one is going to be identical to this one, except instead of a sum, it's going to be a difference. So cosine x, cosine y minus sine x, sine y. And of course, at this point, since this is a positive right outside of the parentheses, those parentheses aren't really doing anything, right? They're performing the associative task, which, you know, the associative property. They're associating terms. They're grouping things, right? But I noticed that if I basically just took down the parentheses, this cancels with that, and I'm left very simply with 2 cosine x cosine y, which is, of course, identical to the right-hand side. And oh my gosh, that was pretty stinking easy. Now, let's look down at this one. And it looks like a mess, but actually this one is really, really easy too. Because if you think about it, what do these two, I mean, basically tangent u plus v and tangent u minus v are identical in their structure, except the plus and the minus are swapped, right? That means if you multiply them by each other, the numerator is going to create the difference of two squares because this numerator is the conjugate of that numerator. The denominators are going to create a difference of two squares because this denominator is the conjugate of that denominator, and you're going to wind up with exactly what you have here. I mean, it's not even going to take very long. So what we have here is tangent x plus tangent y over 1 minus tangent x tangent y, and then tangent x minus tangent y over 1 plus tangent x tangent y. And then when I multiply them out, I mean, it's another one of those ones that looks nasty because it's just notationally, it's just large and involved, but it winds up being a two-step verification problem. You know, it winds up being really nice and tidy. And you know, you can after you get used to using these identities and you gain some facility when using them, you will be able to sort of see these things and make those predictions. Okay, let's go ahead and do two more verification problems before we finish out with a couple of equations. Now, this one right here, obviously, you could start on either side, you know, and we had one like this during the class discussion, and we didn't work on the right-hand side, but let's go ahead and work on the right-hand side just to show you something, okay? And so we have, you know, root 2 over 2 times cosine x plus root 2 over 2 times sine x. Well, that might not seem like it's a step in the right direction, but here's the thing. Root 2 over 2 has a relationship with this pi over 4. And I know that this is cosine u minus v, right? Cosine of u minus v. So if I can transform this side into cosine u, cosine v, plus sine u sine v, then I can actually then change this into that, right? Well, I have, okay, let's say that x is the u. I already have cosine u. Is there a way of changing this into cosine v? And there is. You can change that into cosine of pi over 4, right? And then this is sine u, and then sine of pi over 4, which then very, very easily becomes x minus pi over 4. Now that's important because there are times when you're just given sine plus cosine, okay? If you're just given sine plus cosine, you know, kind of like when we were given that problem, sine x plus cosine x is equal to root 2. Okay, well, we basically wound up squaring this twice, and it was 13 problems. It was 13 steps long or something ridiculous like that, right? Well, we could have just divided both sides by root 2. And if we divide both sides by root 2, you know, I'm then going to get, if I rationalize both of those denominators, something remarkably similar to that, right? And of course, you can flip it around, you can do whatever it is that you want, but here's the thing, it doesn't actually have to go to cosine x minus pi over 4. I only turned it into cosine x minus pi over 4 because that happened to be that. Could I have just as easily turned it into that? Because if I turn it into that and make it sine cosine, it becomes sine of x plus pi over 4 is equal to 1. Well, sine plus pi over 4 and cosine minus pi over 4 are the same thing, right? Because remember that sine is only pi over 2 away from cosine in terms of the graph. If I move one of them pi over 4 towards the other and move the other one pi over 4 in the opposite direction, then they meet, okay? And so what happens here is, when is sine equal to 1? Sine is equal to 1 where the angle measurement is pi over 2 plus 2 pi n, and therefore x is equal to pi over 4 plus 2 pi n. And if you remember, I don't remember whether it was on 0 to 2 pi or negative infinity to infinity. I'd have to look back at the pages. But I do remember that when we got done doing both of the squaring processes, we got pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Now, because we didn't square it, we didn't open ourselves up to those extraneous solutions, and we actually only got the one solution that fits. And that's kind of cool, right? Now, of course, again, if you instead of doing sine of x plus pi over 4, if you had cosine of x minus pi over 4, okay, well, where is cosine equal to 1? Well, cosine is equal to 1 where the angle measurement is 0 plus 2 pi n, and when you add pi over 4 to that, you get exactly the same answer, okay? So this, I mean, it can go to here or it can go to here, depending on what you transform that root 2 over 2 into. If you transform this root 2 over 2 into cosine, you're going to get the sine sum. If you turn this root 2 over 2 into sine, you would simply just have to switch the order of the terms, and you would get the cosine difference identity. But both of them will lead to the same answer. And so this is not just details in terms of what we're trying to accomplish here. This actually does wind up occasionally making something really, really much easier. And I actually have given a problem on a test in previous years where basically it was a extra credit problem. I said y is equal to sine x plus cosine x. Use your identities to transform that and then, you know, identify the parent and list the transformations and graph it. And what you had to do was you had to take that and you had to multiply it by root 2 at the same time that you were dividing it by root 2, thereby multiplying by 1, right? And it wound up being, you know, either root 2 cosine x minus pi over 4 or root 2 sine x plus pi over 4. And whereas, you know, some people would look at this function right here and scratch their heads, it actually, like just with that simple move right there, it winds up being a very, very simple transformation. I mean, you know, stretching by, you know, an irrational number, probably not fun, but doable, right? You can sort of ish it because root 2 is approximately 1.414. All right, let's move down to this one. This one is basically the same as the one that we did with sine of x plus h. It's just with cosine, okay? And so we're going to use the cosine sum formula. So cosine x, cosine h, minus sine x, sine h, minus cosine x, all of that over h. Now again, we're going to identify the fact that the cosine and the cosine probably need to go together, right? And so we're just going to reorder this bad boy, just being careful that you take the sign, S-I-G-N, meaning your positive or your negative that belongs to that term, with it. And so we can reorder this as minus cosine x, and then minus sine x, sine h, all of that over h. And of course, if you sort of group that like that, you wind up getting cosine x, cosine h minus 1 over h, minus sine x, sine h over h. And of course, that is identical to the right-hand side. And so, like I said, a lot of these are just sort of ways of playing around with these values and whatnot, okay? Let's go ahead and take a look at a couple of equations before we call it quits, okay? Now the first one is sine of x plus pi over 3 plus sine of x minus pi over 3 is equal to 1. And we scratch our head and go, shucks, because we would want those to be the same angle measurement. But since we know our sum and difference formulas, we can go ahead and, you know, basically expand it out and get sine x cosine pi over 3 plus cosine x sine pi over 3 plus sine x cosine pi over 3 minus cosine x sine pi over 3 is equal to 1. Now again, because there's a positive out in front of this paren, those parens are basically window dressing, right? They're simply grouping terms. They're not holding a factor at bay. And so those two can wind up being canceled out. And I know that cosine of pi over 3 happens to be 1/2. So this is 1/2 sine x plus 1/2 sine x, which just gives me sine x is equal to 1. And it does. It cleans up that simply, okay? And of course, where is x? Where is sine x equal to 1? Well, where x is equal to pi over 2, and we're going on 0 to 2 pi here, and that is it. And if you're thinking to yourself, gosh, maybe I ought to check that answer. Okay, check that answer. That's fine. When I plug pi over 2 in here, I'm going to get sine of pi over 2 plus pi over 3. That's going to be sine of 5 pi over 6. And when I plug it in here, it's going to be pi over 2 minus pi over 3. So that's sine of pi over 6. Guess what? Sine of 5 pi over 6 and sine of pi over 6 are both 1/2, and therefore your answer checks out. All right, let's go ahead and take a look at this one down here. I don't know, like you can look at this one, you can be like, well, am I going to have to change two things? And the answer is sometimes, unless you can think, 2 or 3 steps ahead, you don't know. So the first thing you really need to do is you really need to reckon with that cosine of a difference. And so that cosine of a difference winds up being this sum, right? Now cosine of pi over 2 is 0. Sine of pi over 2 is 1. So that becomes 1, that becomes 0. So basically this whole term goes bye-bye. And that sine squared, actually, you don't have to do anything with it at all. Now you simply have to factor out the common factor here, and you're left with sine x is equal to 0 and sine x is equal to -1. Now where is sine equal to 0? Well, sine is equal to 0 at 0 and pi, and sine is equal to -1 at 3 pi over 2. And if you really wanted to, you could plug those in and check all 3 answers against the original equation, okay? So that's kind of where we're at with these. I'm hoping that the only limiting factor is the fact that having been just introduced to these sum and difference identities, they're still a little bit new to you. But working with them through the homework and continuing to work with them as we move on to double angle identities tomorrow and do some mixed practice on Thursday, I'm hopeful that by the end of the week these ought to be pretty well ingrained into our memory, at least our short-term memory, such that we can continue to use them. And thankfully we're doing this towards the end of the summer so that they'll be fresh in our minds when we start calculus in August. Okay. As always, if you have any questions, please do shoot me an email or a message through Teams, and I will get back to you just as soon as I can. Bye-bye.